Hello, class. Welcome to the next section, chapter 9.6. Today we are going to go over more numerical methods. So these are methods for approximating an integral. We saw a few of these methods already back in chapter 7, where we were doing left hand and right hand Riemann sums, as well as the midpoint formula for a Riemann sum. Uh, it would be, if you're fuzzy with that, it would be a great time to pause and go back and sort of review that stuff before we move on. Although it's not necessary, but it definitely would help. So let's go ahead and get started. So again, in chapter 7.1, we covered the basic numerical methods for approximating the area under a curve. Um, we use those to figure out what the formula for a limit is, right? Or for an integral is, right? So we took the limit as the number of rectangles under our curve went to infinity, meaning they got smaller and smaller and smaller and smaller, infinitesimally small. So you can think of that as just kind of like coloring a graph under, between this axis. And that's how we formed the definition of an integral, right? By looking at those Riemann sums and taking the limit as it goes to infinity. So quick review. The left-hand sum means that we start on the left-hand endpoint. So if we're going from integrating from A to B, we would start at A as our place where we evaluate the height of our rectangle, right? The height of our function. The right-hand sum means that we're ending at the endpoint B. So we're actually taking the right-hand endpoint. So here, if we were plugging I, you would see we would start with, I'm sorry, if I plug in 1 for I, you see that this turns into X naught, the leftmost entry point A. For the right, it would be the first evaluation would be the right-hand endpoint of the square. So that would be at X1 instead of at X naught, right? So we're evaluating everything on the right-hand side here, everything on the left-hand side. Both of these approximations led to the exact same integral, right? Again, because it doesn't matter if we're going left, right, or anywhere else. We're taking the approximation as these uh, go to infinity, okay? Our delta x here was just me taking my interval and dividing it up into n parts. And that's how I figure out which values I plug into my function, okay? We saw that a better approximation to the left or the right-hand sum was the midpoint rule, which we covered in 7.2. Okay, the midpoint rule means that we're looking at the average value, um, the average endpoint between the left-hand and the right-hand endpoint, and that's the point we are evaluating into our function to get the rectangle height. So I'm not taking the left-hand side of the rectangle. I'm not taking the right hand side of the rectangle. I'm taking the value directly in the middle of the right and left hand side. Okay. So each one of these xi bars is just the average distance between a left endpoint and a right endpoint for a rectangle. Okay, so it's the point right in the middle. So in this section, we're going to cover two more methods for approximation, and we will look back on these left hand and right hand and midpoint approximations, and we'll compare them all. Okay. The first one that we're going to talk about is the trapezoidal rule. Okay, so here we're using trapezoids in order to find area under a curve instead of rectangles. And now, before I even get further than that, that might make more sense to you because if you think about a curve, one side is always higher than the other, generally speaking, when we're forming these rectangles. That's why we choose either a left-hand endpoint or a right-hand endpoint. However, we use a trapezoid, we don't have to choose either, right? Everything will be uh, a closer approximation to our function height, okay? So the trapezoidal rule is the average value for the left-hand sum and the right-hand sum approximations. So I'm going to take the left sum, I'm going to take the right sum. I would add those two outputs together, those two approximations, and I would divide them in half. I find a halfway point between those two. And that is my trapezoid rule. Now, if I actually plug in the formulas for the left hand and right hand sum, we can start to develop an actual formula, right? So right here, I just have the summation notation. Again, left point and right endpoint. If I start to actually expand this, remember this starts at x naught and this starts at x1. the last value I plug in is x sub and minus 1. So 1 before the last terminal point of b. Here I would plug in f of xn. This would end at n. So looking at that, we just kind of plug that in, the first few couple of terms, x naught, then x1, x2, x3, so forth, and ending at 1 before the endpoint, n minus 1. This one starts at 1, 2, 3, 4, etc., until I end at the very end endpoint. Now notice what happens. From the left-hand sum and the right-hand sum, everything gets repeated twice, except for the first term and the last term, right? The second term for the left is the first term for the right, so that happens twice. So forth and so forth and so forth. The last term for the left-hand sum is the second to last term for the right-hand sum. So everything happens twice except for the two endpoints, x naught and xn. Okay, so everything else happens twice except for the endpoints of those. So let's go ahead and finish simplifying these out. Okay, well, I guess that would be the final form for that. So let's look at what this looks like geometrically. So if we were to draw our curve and look at the left and right hand point endpoints. This is basically just the line that connects those endpoints, right? So let's say this is for some bar, its left endpoint. For some bar, this is its right endpoint. This would be x bar I, right? That midpoint value that we would use for the midpoint rule. Okay. For the trapezoid rule, okay, we have a base, we have a base, we have our height, and this is the slant line. Okay, so remember what your area is for trapezoids. Base 1 plus base 2 times the height, okay, divided by 2. So if we compare this to the midpoint rule, what the midpoint rule is doing is evaluating right at xi, and I just draw a regular rectangle. Okay, so the trapezoid rule connects the left and right endpoints with a straight line, and you can see that would be better than a left-hand triangle or a right-hand triangle, right? And so the midpoint, if we go back and do this, it is evaluating right at that middle value for height, okay? So what I'm claiming here is that at this point of the midpoint, the area of this midpoint rectangle is equal in area to if we were to draw a tangent line that was tangent at the midpoint and drew a trapezoid over that, right? So at xi bar, right, at the midpoint, if I drew a tangent line, okay, that stopped at the left-hand endpoint and stopped at the right-hand endpoint, and I turn that into a trapezoid, these two shapes have the same area, okay? The area here in yellow is the same as the area in red or pink, right? This overlapping area, right? So the midpoint rule, every rectangle is equal in area to a trapezoid whose oblique line lies tangent to the curve at the midpoint. If we compare these two trapezoids, okay, so I'm saying that they're equal, and generally math, I can't just say something, I have to kind of verify that it's true. So if we compare the two trapezoids, then we're going to have the following, okay? So this is my trapezoid, and this is the trapezoid that has equal area to the midpoint formula. So as you can see, one is an underestimate, one is an overestimate, but if we had to compare them, okay, it seems that this midpoint rule area is a better approximation, right? There's kind of a big gap here. The amount that's over doesn't appear to be as large as the gap formed from this underside, right? So this area is not as close an area, true area, as the red one, okay, the pink one, right? So from appearances, at least, the midpoint rule, right, the tangent line trapezoid appears to be a better approximation than the standard trapezoid rule approximation, okay? So let's do an example. We want to verify that the area in each rectangle from the midpoint rule is equal in area to the trapezoids formed with that oblique slant line tangent to the midpoint. Basically, this example is prove that this is true, that this area and that area are the same, right? So that the midpoint rule rectangle and the tangent at the midpoint line trapezoid have the same area. Okay, that's what we're doing here. So remember, from the midpoint rule, if we're looking at just a single rectangle, that's really what we're going to do. Is we're going to just compare one rectangle with one rectangle, obviously generalized for all true rectangles of that kind. So for the midpoint rule, a single rectangle is the width of the rectangle, delta x, times my function evaluated at that midpoint. So the tangent line at x bar intersects our function f of x at the point x bar, and then the function evaluated at x bar I. Okay, so I'll just say x bar, but we know this is for it's not a specific one, that's why it's sub I, but I'll just say x bar. Okay, so the midpoint x value and the function evaluated output at that x value, right? So every tangent line at x bar has this point. If we plug that into the equation of a line, remember, equation of a line is y equals mx plus b. Okay, I have y, my output, equals m, the slope at that point x bar, x plus b. Y equals mx plus b. Slope is the derivative of our function at that point. Okay, that tells us the rate of change. Times our x value is going to equal my output value, right? Plus b, some y-intercept, right? So this should be familiar to you. So if we change this, so this is the line that this point satisfies, okay? We would like to turn this into something that represents our tangent line. So we would really just need to know this b, okay? All points have x and f of x. The slope is f prime at that point. So if I solve for b, I take that y value that I have and I subtract the derivative at that point times the x value for that point, right? Basically, I'm just getting b alone. So remember, when you're finding the equation of a line, y equals mx plus b. If you have a point, you plug that point into your function and you solve for the y-intercept. And that's basically what I'm doing here. I know what the slope is. I know I have an x and a y, or output. I plug it all in and I solve for it. So the equation for my tangent line then is the slope at that tangent point times x for any point. Okay. So remember, this is for a line now. And then this is my b. My b is f prime of x minus this whole thing when I move it to the other side. The slope at the midpoint times the x value for the midpoint. So this is the equation of my tangent line. This is y equals mx plus b for each tangent line. So at each midpoint, I would just substitute the different x value for that midpoint. So also, now that we have the equation for a tangent line, we've got to do the same thing to find the equation for the area of a trapezoid or any rectangle under my curve within that interval, right? So for any trapezoid, the area is 1/2 h times b1 plus b2. b1 would be the evaluation on the left endpoint, that would be one base. b2 would be the evaluation on the right endpoint. H is the same thing as the distance between my left and right endpoints, and then 1/2 is just 1/2. Okay, so again, let's go back here. Okay, so remember, we're doing the trapezoid that is tangent at xi. So the function height for one base is given by xi minus 1 being plugged into the tangent line. The other base is xi being plugged into the tangent line. Okay, because it's this pink triangle here. And the distance between them is delta x. All right. So B1, this is what I get when I plug the left-hand endpoint into the tangent line. B2 is what happens when I plug xi, right, the right-hand into the tangent line, h is delta x, and then 1/2 is 1. So the length of our bases of our trapezoid are given by the tangent line, right? So I plug in xi minus 1 and xi, the left and right hand sides, to the equation of the tangent line that I just found to find what base 1 and base 2 are for my trapezoid formula. The area of the trapezoid formed by the tangent line then is me plugging these things in. So the area is 1/2, h is delta x, okay? B1, so I'm plugging in xi minus 1 to that formula. The only, okay, everywhere I plug stuff in is this x. The x sub I is a fixed constant for each rectangle, but this x is what's changing, right? This is what helps me pick each rectangle. So I gotta find the evaluation at the left endpoint. So I'm plugging in the x I minus 1, right? This is still xi bar, xi bar, xi bar, xi bar. Okay. I will add to that me plugging in B2, which is this x sub I. Okay. This is still x bar, right? X sub I bar, x sub I bar, x sub I bar. So this is the area for each trapezoid where the slant line or the oblique line is tangent at the midpoint. Okay, I'm going to repeat myself over and over again so that we're very clear on what these calculations are. So when I start to simplify stuff, right, all of these things here are the same. They don't change. They're a constant, right? It doesn't change because it's still the same slant line. So those are same. What's changing here is the f bar, x sub I bar, or f prime, I'm sorry, times xi, and then in this case times I minus 1. So these two I can kind of put together and say there's two of them, right? I have two f x sub I bars, one here and one here, and I have two of these parts, okay? These two parts, the first parts in B1 and B2 calculation, are different. One is x sub I, one is x sub I minus 1, one less than that, right? Left endpoint, right endpoint. Okay, we got the delta x and then 1/2. So now what I want to do is I want to try to finish combining things, right? So I like to factor. So possibly we factor some things out, or let's see, what do we do here? Right. So I factor out the f prime on the x bar and the xi minus 1. We keep this as 2, right? So that looks pretty good. Let's see what else we can manage to do here. So here I moved in the 1/2, and I divided each of these by 1/2, right? Okay. So here I multiply this into the parentheses, so I get half of this. This turns into 1, and this turns into 1. Okay. Now, if you look at this very closely, left endpoint plus right endpoint divided in half is the same thing as xi bar. So I could change this into xi bar. Okay. F prime xi bar times xi bar. So again, if you're like, what? This part right here. This is the only thing I changed. This is the definition of the midpoint, right, that we've been using. Everything else stays the same. But look what I have. I have an f prime xi bar and an f prime xi bar and another one and another one. Okay, so this term and this term is identical. One is positive, one is negative. So all I'm left with is this delta x now, f of xi bar, which we know from the beginning is the area of a single rectangle from the midpoint rule. Okay, so I have shown, right, this is the end of that problem. So what I've shown then is that the area, what we started off with, right, this thing, the area of a single rectangle from the midpoint formula. And then I found the area using this. Okay, this is the single area from that same rectangle of the trapezoid rule with the tangent line at the midpoint, tangent to the midpoint. And when I derived this, I ended up with the same thing I started with. Okay, what I was comparing it to, I should say. So this is the area of a single rectangle from the midpoint rule. So in section 7.1 and 7.2, we had an example. We used the same example in both. In 7.1, we use the left hand and the right hand rules to approximate the area for x cubed minus 3x squared from 0 to 1 with n equals 4. And in 7.2, we did the exact same thing, but we did it with the midpoint rule. And we're able to show that the midpoint rule was more accurate than the left and right hand sums. Okay, so let's summarize what we had before from those beginning sections. So again, you can go back and check and verify. But my left hand sum for that 4 rectangle approximation was negative 0.515625. Okay. My right hand side was negative 1015625, so it was an under approximation. My midpoint rule gave me this as the value out. And if I go ahead and throw in the trapezoid rule, right, the left hand side plus right hand side divided by 1/2, I get 0.65625. Okay. The exact value that we found through calculating on our own was negative 0.75. Okay. So if this was the real value, the left-hand sum was about 0.25 off. The right-hand sum was about 0.25 off. The midpoint rule was very, very close to 0.75. And the trapezoid rule, which we did not have to find independently, we could use the left and right-hand sum since we know it's just the average of those two, was very close as well. Okay, but was it closer to the midpoint rule or farther away from the midpoint rule? That's when we really have to compare. Okay, so we can make a table so that we can see a little bit more clearly what's going on. So when n equals 4, this was my left-hand sum, right-hand sum, the midpoint, and the trap. And again, the real value is negative 0.75. That's not going to change. If I do kind of look at these without looking too closely, this was close up to this point right here. So I was about 0.008 under. Here, it's 0.765, so it looks like I was 0.001 over, right? Because it's 0.65. So the midpoint rule was closer than this one. I guess that would be 0.15. Okay, this is 0.15, and this is just 0.008. This is 0.015 off. So the midpoint rule was more accurate than the trapezoid. Before we get into this, let's just go back one more time and look at that, because that should be what we would think. This is the trapezoid rule. It connects the left and right endpoints. The midpoint rule was the tangent line. So again, the midpoint rule, its trapezoid, you can tell is a lot closer. It's an overestimate, but it's a lot closer in value than this was. This kind of has a big gap, whereas the midpoint rule does not. So again, here it's hard to tell because you have a big overestimate, a small underestimate, and a larger overestimate here. So it's kind of like, well, it's definitely over, but how much? But if we compare them in the trapezoid rules, you can see that the trapezoid versus the midpoint trapezoid, um, that's what I'll call it, is much, much more accurate. So the midpoint rule, just from looking at that little portion of the graph, it looked like that should be true. And from this calculation, we're able to compare and say that it is true, right? So again, putting all of these in, let's say I double the size of my rectangles from 0.51 to 0.62. That's much closer to 0.75. From 1 to now being 0.87, that's also much closer to 0.75. This was 0.72. So it's like 0.008 away. Now it's 0.002 away. That's much, much closer. This was going from 0.015 away from 0.75 to now being very, very close, right? 0.753. So this is 0.003 off, and this is 0.002 off. So the midpoint rule is still closer, right? So it shouldn't change actually which one is closer or not. So my left-hand rule now, with doubling again at 16, I am closer to 0.75, but still far away. Right-hand rule is 0.81. It's still pretty far away, but it's closer than it was. It's edging in the larger the end goes. The midpoint rule is very, very close. 0.01 away. Okay, actually that's like 0.0005 away, and then some more. And then this one is 0.0001. Okay, so very, very close in value here. Okay, to our true value. Looking at the errors, since we know the exact value, instead of guessing, we can actually just write those down, right? So when n equals 4, the error in the left-hand sum is negative 0.23, positive 0.26 for the right-hand sum, right? This is larger over it in the negative. This is less over it. The midpoint rule is 0.007 as an error, so 7, so it's 10 hundredths, 100,000, or thousandths, so it's basically 7 thousandths off. And then this is in the tenths, or I'm sorry, the hundredths off, right? So the midpoint is much more accurate. We just jump to 8 and 6. You can see left hand and right hand sum are pretty much the same, accurate as well, 12 and 12. And then out a few decimal points is where you see the difference. The midpoint rule and the trapezoid rule, this is still smaller, right? 0.001 versus 0.003. So basically 002 and 004. And then when we get even more accurate with n equals 16, you could see that the error is getting smaller for both of these. These are both about 0.06 on both sides. Here, I'm 0.0004 versus 0.0009 away from the true value. Okay. So the midpoint rule is closer in value than the trapezoid, and is closer in value than the left or right hand sums. Remember, trapezoid is the left and right hand sum average, so that's pretty good, right? It's kind of a less work, but the midpoint rule is more accurate so far. So as we look and compare the errors, there's a few things, okay? So as I was reading this out, one of the first things that kind of pops into my mind is that the left and right hand sum is pretty much the same. 12 and 12, 20 something, 20 something, 0.06 something, 0.06 something. But one is always negative and one is always positive. They're always different in sign, okay? So number one, as n goes to infinity, meaning as I take more and more squares, right, rectangles, my error gets smaller. And this is true for all of them, right? As I get more rectangles under the curve, the error that my summation gives me, my approximation gives me, is smaller. That should be apparent because when we take n going all the way to infinity, right, there is no error. Error goes to 0, and it's an exact value. Number two is that the error for the left-hand sum and the error on the right-hand sum are approximately equal, but opposite in sign. So I did point that out already. Notice that when we double the value of n, right, 4, 8, 16, the error in the left and right is halved. Okay, so let's go ahead and note that. So I started with 0.23. Just about half of that is 0.12. Just about half of that is 0.6, right? Same thing here. 0.26, just about half of that. That's just about 13, right? 128. Half of that is 0.06, so half of the 12, right? So they're approximately equal, opposite in sign, and every time I double up, my error basically halves, right? So that's pretty good thing to understand, right? Similarly, if I go more than that, instead of just going like from n to 8, go from, I'm sorry, 4 to 8, go to 4 to 16 instead. I increased my n by a factor of 4, so my error decreases by a power of 4 as well. Okay. Notice that the error for the trapezoid rule and the error for the midpoint rule are opposite in sign as well. One of these is an overestimate and one is an underestimate, so they differ in signs. As, if we go all the way back here, we were able to tell here, oops, okay, underestimate, overestimate. Okay. That will generally be true because remember the secant line is tangent, so it's not always true, but it's true for our example right now, right? So this shouldn't be a surprise because we saw in our drawings that the general trapezoids are the midpoint and trapezoid rule earlier. We kind of saw one was over and one was under. The error for the midpoint rule is about half of that as the trapezoid rule. So back to errors. This is 0.015. About half of that would be 0.007, right? 7.5 really. Half of 0.0039 or 0.004 would be about 0.002, right? Half of 100, right? It's like 0.0050. So they're very close. This is half, about half of the trapezoid. So um, that's actually pretty good, right? We have half of the error. So this confirms our observation from the graphs that we had earlier that I've gone to a few times, that the midpoint rule is more accurate. And in fact, it's about twice as accurate as the trapezoid. Okay. Notice that if I double the number of rectangles for the trapezoid and for the midpoint rules, the error decreases by a factor of 4. So every time I double, my error decreases by 4. It's a quarter of what it was. So if I'm going from 4 to 16, that is the error is going to decrease by 16. So again, we just look here. From 4, when I double it, okay, the error is a lot different. If this was about 80, then this is about 20, right? So a factor of 4. This is about 80. This is about 4, right? So that's about almost 20, right? So 0.007, 0.007. So which was 16, right? We were saying that it was 16 is about what happens when I go from n from 4 to 16. I go by another 4, so it decreases by a power of 16. So that's pretty accurate. Okay. Same thing here. From 15 to 3, so um, that's about 5, right? So by a fifth, decreases by a fifth or 20%, um, which is next close to a quarter, so close to a fourth. And then if we go to the next, double that, that's about a 16th of that amount as well, right? So this is about 16, so that's why this is about 1. Right, so very interesting in looking how the errors uh, are related to each other. This is something we look at a lot in what's called numerical analysis. So for anyone that wants to be an engineer or a physicist, this is a big part of what you do, is looking at error tolerances and how error accumulates. There you go. So for error of n equals 16, it's about 1/16 the value of the error we had from 4 rectangles, which we saw. So let's look at error, okay? What is error? Error is how much you're off by. So your error is your exact value minus your approximation, okay? If I ever said, hey, it's about 2 miles from my house to the store, but in reality, it's exactly 2.1, well, I'm off by 0.1. How do I find the error? I took the exact value and I subtracted off the approximation. Whatever was left, that's how much I was wrong by, right? So it's the same thing in math. I take my exact value, which is my integral, and I subtract my approximation. Same thing here for the midpoint rule, left-hand rule, right-hand rule, it's all the same. I take my exact value and subtract my nth rectangle approximation. So let's look at trying to bound my errors. So this is something new. I don't think we did this in the left or right hand sum portion, but generally when we're talking about errors, we would want to know what's the largest possible I could be incorrect by, right? If I know the largest I could be incorrect by, it gives me an idea of how many decimal points I need to use to be accurate and how many ends, right? How many rectangles do I need to use in order to be this close to the true value? The reason for this is that, remember, some integrals are impossible to solve, and the only way to solve them is to use a numerical approximation. And if I want to make sure that I'm within 0.00001 of the true value, well, how many rectangles do I actually have to need, right? I would like to use the least amount of possible. If I can be very, very close to the true value with 5 rectangles, why would I use 10, right? So bounding my error is good for me because it lets me know how much work do I actually have to do in order to be good enough, right? Which, as a lazy person myself, that's exactly what I want to know. So the following formulas give us a way to bound the errors for our approximation. This lets us figure out the maximum error possible that our approximations may have with the number of rectangles that we're using. This is very, very, very useful for numerical methods, especially if you are coding programs and you want your machine to always be within 0.000001 of the true value. Your code only has to make sure that it's that accurate. You don't have to be more accurate than that, right? So if you're into computer science, for instance, there are floating decimal number approximations forever and ever and ever. When you use calculators, the same thing, but it's always accurate enough that you'll never even see the errors come up, right? So it's very good and important for programming things and building bridges and stuff like that, right? So if I'm designing something that has parts that must fit to a certain accuracy, I want to know that my maximum error is below that tolerance, right? So imagine designing a top for a water bottle and it doesn't seal well. And every time you move around, your water spills all over you and out of your water bottle. That's not a very well-made water bottle, right? You didn't design the cap to fit well enough because you didn't calculate the error tolerance for your top that you were designing, okay? So now imagine the same thing, but when you're building a bridge or a building or a train or an airplane or a rocket, right? Those errors can cost lives, and they have, right? It has. People have died from miscalculations and not calculating the errors correctly. So let's talk about how to do this. What we need is a couple of derivatives, right? As you can see here, I need the second derivative of x to be less than some value k within my interval of existence, right? I'm integrating from a to b. So over that interval, I need the absolute value of my second derivative to be capped by some number. Okay? Now your first thought is probably like, where the hell did this second derivative come from? Why do I have to use that? Well, how is that the measure? It doesn't really matter. And it's not always the second derivative. Sometimes it's the third, fourth, fifth, or sixth derivative. There's different ways to calculate this value, which we're not going to get into in this class, but we do talk about that in my differential equations course. There is a video series for that. If you're that interested in it, you can take a look at it, but at this point, this level, you probably wouldn't understand anything I'm talking about, which is okay. Hopefully, you get there at some point in your careers as scientists and mathematicians. So for now, we have the second derivative, and I need the absolute value, and I need it bounded by some value. I need it to always be less than some constant, okay, over my interval. That doesn't mean forever, just over my interval, okay? So if I can do that, then for my trapezoid rule, my error will always be less than, so the absolute value of my error, so whether it's below or above, it will always be capped by this value. So that value k times the length of my interval cubed divided by 12 and the number of rectangles I'm going to use squared. Okay, so my error would always be smaller than this. Right, so now I have a way to make sure I know how accurate I need to be, right, which we'll talk about here. For the midpoint rule, which is more accurate, to calculate its error, it's the same way, but it's 24 times n squared. And this comes from looking at our errors, right? Remember, the error in the midpoint rule was always half of that of the error of the trapezoid. So that's why the values between 12 and 24 here are doubled, right? Or halved, however you want to look at it. Okay. So the last numerical method we're going to look for, so you might say, Professor, I thought we were going to go over this. We are, but we're going to see this again. So let's go into the next method. So that was our first method. Our next method is the Simpsons rule, okay, it's named after the person who created it. And now this one is a little bit different. So we've been using standard geometric shapes in order to find the area under a curve so far. We've been using rectangles and either looking at the left sum, the right sum, or the midpoint in order to figure out how tall I need my rectangle to be. Or we were using a different geometric shape that kind of came naturally, the trapezoid, which we just drew a line to connect the left and right endpoints. And that was how we did it. But it was easier to find that. We just found the left sum and the right sum and divide them in half, right? Or find the midpoint between. Simpson's rule is different. We're not using a standard geometric shape here, okay? We are going to be using parabolas, right? So we're going to be using parabolas. And what we're going to do is we're not looking at any one rectangle under our curve. So I'm not looking at a left endpoint or a right endpoint. I'm actually putting two rectangles together, and I'm using the left endpoint of one and the right endpoint of another, and the connecting point, the point right in the middle of those two. Okay. So since I'm using two rectangles at a time, every time I do this, and again, you might say, what are you talking about? It doesn't worry, we'll draw a picture for you in a second, right? But I'm using two rectangles at a time. And since I'm using two rectangles at a time, I need to have n be an even number. Because if it was an odd number, I'd have one lonely rectangle sitting there that I wouldn't be able to use since I use two at a time. Okay. So every two sub-intervals, again now, get combined into one. And the point in the middle of my new sub-interval is the vertex of my parabola. Okay. So the left endpoint is one point that my parabola goes through. The right endpoint on the rightmost rectangle is a point on my parabola, and the point in the middle of those two rectangles is the vertex of my parabola. Okay. Uh, Parabolas are easy to integrate, right? It's easy to find the areas under the curve. So we integrate the area for every two subintervals, right? And we combine that to make one subinterval. So if this is my graph, it'll be easier to see this. I got my leftmost endpoint, I have the right endpoint, and then I have the endpoint for the next rectangle. So there's two rectangles here, right? And so those 3 points then give me enough information to draw a parabola. If I want to draw a parabola from scratch, I need at I need 3 points on the parabola, or I need 2 points with one of those points being the vertex. Okay, you can review my algebra stuff if you're like, what really? We do that a lot in my algebra and my pre-calculus stuff. Okay, so I have 3 points. That means I can draw a parabola to fit those lines. Okay, so it doesn't have to be the vertex, as I said earlier. Apologies on that, but those 3 points are enough points for me to create my parabola. So the area under one parabola is always ax squared plus bx plus c with the differential in x. And again, that's from xi minus 1 to xi plus 2. The only problem is I don't know what the a, b, and c's are for each parabola. Each one's going to change, right, depending on how the function is. However, in general, I know that every parabola passes through xi sub 1, that's the leftmost, and its output. The shared wall, I would say, okay, for the two rectangles, the one in the middle, x sub I, and the rightmost of those two rectangles, the xi plus 1, and its evaluation of my function. Okay, the area under a parabola given by the integral from the first point to the last point of a general parabola looks like this, right? This just goes to x cubed, x squared, this gets an x, and we have the reciprocal function. And let's plug in our values so that we can find the area under a general parabola. Okay, so I have xi plus 1, which will be cubed minus this cube point. So basically, it's kind of like I wrote the two out and pulled them out, or I could just kind of subtract them in line. So then I'll have the b with x squared minus x squared, and the c with the two x's being subtracted. Okay. From here, I can't do much here. I don't want to just distribute and expand everything. Okay. But I do have formulas I can use, like this. This is a difference of squares. I could factor that. This is the difference of cubes. I could factor that. Okay, so a difference of cubes is the first term minus the second term, and then almost looking like the expansion for a perfect square, but there's no 2 in the middle. So you get square the first term, square the last term, multiply the 2 together, but you do not multiply it times 2. You don't double it. Okay, you just add those all together. So that's the difference of cubes factored form. I have the difference of squares and its factored form. So 1/2b x minus x plus 1 minus x I minus 1, and then here, same thing, but added. And for the c, I just don't do anything with it. Now, I know, so I would like to continue factoring if I can. I really want to simplify all the way. Whenever we have polynomials, we're always looking to factor, especially things that are already factored. So notice that I have this xi plus 1 minus xi minus 1. I got it on the second term. Okay, so it's in the first term, it's in the second term, and it's in the final term. So at the very minimum, I can pull that out. So I can pull out this xi plus 1 minus xi minus 1, and then just write everything that I had left, right? So I have 1, 3, 1/3 a times the second part of the expansion plus 1/2 b times this plus part, and then here is just plus c. Okay, so I have the a portion plus the b portion plus c. Now from here, I could not factor at all unless I distribute this 1/2 b and this 1/3 a. Okay, so I'm going to go ahead and pull out the constant portion of those that I can first so that everything becomes whole. So I'm going to multiply, well, I'm looking at 2 and 3. Okay, 2 and 3, the common denominator there is 6, so I'll pull out 1/6. When I pull out 1/6, okay, this turns into 2, right? Because pulling out, so it's 1/3 divided by 1/6, so that would be 6/3, so that's 2. If you're not sure, you could just be like, okay, well, what times 1/6 will give me 1/3? Well, if I multiply it times 2, those cancel and I get 1/3. Okay. Same thing here. If I pull this out, I'm multiplying by the reciprocal, so that'll be give me 6 times 1/2, so that's 3, right? And then this turns into 6 because 1/6 times 6 will give me back to 1. So that's good. So now, now I want to distribute the A's and the B's, right? So I kind of do this one at a time, especially with this fraction stuff. People find that fairly difficult to follow, so we did that one at a time. Next, let's distribute these A's and the B's. Okay, so I distribute 2A everywhere, and I distribute 3B everywhere. I haven't done anything else, but just put 2A in front of everything. So now I can pick apart the things that are the same. I can start to try to separate stuff if I can. My goal is to factor. But with A's and B's, nothing is the same, right? I have this bxi plus 1. I don't have any other just xi plus 1s. This is a minus 1. This is just a 1 plus I. This is the I minus 1, but it's squared. I do have one xi minus 1 here. Okay. Oh, I'm sorry. It's attached, right? This is the xi plus 1 times an xi minus 1, so I can't break those apart. And I have a AXI plus 1. So now we're just going to be kind of tricky here. And I'm going to try to group things together, right? So I have this I plus 1 term. I have an I plus 1 term here. So this term and this term should probably kind of like come together since they're similar values. If I have a squared term and a term with B, well, this one is a mixed term. So let's just kind of reorganize things a little bit, okay? So I still have this, that's still here, the 1/6 times the first part. I have the ax squared I plus 1, and I added another one of these I plus 1s. But notice, I added only one of them. I only moved one. I have 3. So I took one of the a's and one of the b's and one of my c's, right? So here there's 6 c's, there's 2 a's and 3 b's. Here there's one of the a's, one of the b's, one of the c's. Here is one. Here this, so again, they're mirrored. This one, there's 3 of this ones, 3 of these ones, 2 and 2, right? So just kind of keep track. If you have to write up in front of you, it's really easy to see what's happening here. Okay, so I have an A, I have x squared bx plus c. I have another x squared, ax squared bx plus c. This one has the I plus 1s. This has the I minus 1s. And for the last one, I just kind of write everything that's left, right? I have the I plus 1s squared. I have this I minus 1 squared and a mixture of the two plus 2 of them. And it's all A's. Okay. And then here for this last one, I have this bxi plus 1, bxi minus 1, and a 4c. So this first one is a parabola evaluated at I plus 1. The second one is our parabola evaluated at I minus 1. Okay. And then here we have, I'm sorry, this one right here, this one squared. This is nothing for us yet. Okay. So we put these together, put this together. This looks like a perfect square to me, right? Square the front, square the back, multiply them together and double it. Here, I just factored out this 2b term. Okay, one is a plus one is a minus, and then I still have my 4c's. So again, my parabola evaluated at x plus I, my parabola evaluated at x minus I, a perfect square, and this is just a term for me, which I can use in a little bit. Okay, so all I did was really factor this perfect square term here. All right, and notice that I was able to pull out this a. So I have a perfect square of xi plus 1 and xi minus 1, 2b times xi plus 1, xi minus 1, and 4c's. All right, so this is looking like another parabola where I'm plugging in um, almost the midpoint, right? I'm not quite there yet for the midpoint. So again, note that this xi minus 1, f of xi minus 1 satisfies our function in our parabola. So that means that if I rewrite f of xi plus 1, I can replace that with the parabola form, right? So this parabola form here, I can just write my function evaluated at I plus 1. And so if I do that for everything I have my 1/6 in front with this difference of the values. I have my function evaluated at I plus 1, my function evaluated I minus 1, right? Because it's ax, bx, and c with the I minus 1 terms. And then these stay the same so far. So this is a, this term squared, this is b, this term, and plus c. Note that this xi plus 1 and this xi minus 1 is the same as delta I, okay, 2 delta I, because if I find the difference and um, divide it by 2, that would be delta x. Since our parabola spans over 2 intervals, okay, it's 2 delta x's. Apologies for that, right? So from the leftmost to the rightmost, that distance is 2 delta x's, because remember, I have 2 rectangles each time. So this 1/6 is really 1/3 delta x. Then I have my function evaluated here, and then this stuff that's kind of just been trailing along so far, now we're going to start to manipulate some more. Okay. Remember, xi is halfway between I minus 1 and I plus 1. So if I can find an I minus 1 plus I plus 1 and have a half in front, that is my xi, right? So we're kind of there with this, right? And we're kind of there with this. So let's manipulate this and say 2 xi's is one of these, okay? So now I can replace this with a 2 xi. This, right? There's 2 of them, so this would just be bxi and then I have 4c. Okay. So at 1 plus I and 1 minus I, and now I have an a 2xi squared, here a 2b, 2xi, and a 4c. So if I multiply this out, I have now a 4xi squared, a 4bxi, and a 4c, which means I can pull out a 4. And now I have my function evaluated at x sub I. So I have 1/3 delta x, my function evaluated at the rightmost of the two, the leftmost of the two, and 4 times the function evaluated at its shared uh, wall, its shared side. Okay. So if I just move stuff around so that it goes first, middle, and last now, right? Left, the middle, shared value, and the right value, it looks like this. Okay. So each shared end of a subinterval is evaluated twice. So if we go all the way back here, Okay. So each shared point gets evaluated twice, right? So I would draw a rectangle here, and then when I move on to the next one, I have this one, and this one. So it gets used one more time. Okay. Let's see. Question that. All right. So each shared end of a subinterval is evaluated twice. Apologies. So the ends. Okay. So this one and this one. And then when I do the next one, I'm going to have this one again plus two more. So then that's why this one gets used twice. It gets once here. And then when I go to the next two, 1, 2, this is the endpoint. This is the leftmost endpoint for the next two. Apologies on that. All right. So Simpson's rule, if we break it down to its finest components, it looks like this. The x naught, the first term, very first term, gets evaluated once. The next value, x1, gets evaluated 4 times. It's a shared point. And then the next endpoint happens twice on the first iteration and the second iteration. Okay, and so forth and so forth and so forth. So this is a little bit harder to just remember what it is. I always have to keep this formula out. Even if you do remember the formation of this, it could be rather taxing to keep up with. Okay, so remember n has to be even. Okay, note that Simpson's rule is a weighted average between the midpoint rule and the trapezoid rule. I'm not gonna verify this for you. Maybe I'm making you verify this. But 1/3 times the trapezoid rule with n rectangles plus 2/3 the midpoint rule with the same number of rectangles is equal to the Simpsons rule with 2n rectangles. So if this is 10 and this is 10, this would be 20. Okay, this would be 20. I would say that that's actually 5. So I'm a little confused on that. Okay. So my error bound for the Simpsons rule. If I'm using the Simpsons rule, I need the fourth derivative of my function, and I need to bound that by some constant value k between my interval of a and b. So that error is then bounded by k times the distance of the interval to the fifth power divided by 180 to the n times the fourth power. This means, right, there's a very small number here, n to the fourth times something times 180. That means my error will be very small for Simpson's rule. Okay, so let's go ahead and do an example. We're playing with Simpson's rule with errors and things like that, so you guys know how to do this a little bit. Okay, so let's use this previous example I had of f of x was x cubed minus 3x squared with n equals 4 from 0 to 1 to get the following. I'm going to have, so if n equals 4, I'm going to just have my breakdown just like normal, right? So Sn is from 0, 1/4, 1/2, 3/4, and 1. Evaluate these things, okay, into this function. So 1/3, 1/4, and 9, okay, which is -3/4 as an answer. Okay, 3 and 9 is 3/4. So if I evaluate this, I get 9. This 1/3 is from Simpson's rule. This 1/4 is the delta x, right? 1 over delta x. 1/3 delta x. So b minus a over whatever, right? So in this case, 0 to 1 over 4. So that's where the 1/4 comes from. I plug in my values and I get 9. And I get my exact value with n equals 4. Whereas if we come all the way back here to Simpson's rule, trapezoid's rule, and all this stuff for the same exact problem, I had 16 rectangles and I never got the exact value. I got close. I got within 0.000 of the true value, right? Within 1,000th of the true value for each of these, for the midpoint and the trap, okay? But I didn't get the right answer with 16 rectangles. With Simpson's rule, with 4 rectangles, I all the way back to answer. I got the exact answer, right? And so what's happening with Simpson's rule, right? Yeah, it's n rectangles, but we're counting each one as two. So with n equals 4, it's really just kind of two big rectangles, right? I went from 0 to 1/2, and another one from 1/2 to 1. So I'm using half the amount of of rectangles, but actually there's still 4. I'm calling every two 1, right? So this is still n equals 4. And I still break it down to 4, but the accuracy wise is where we get this uh, this little comparison right here, right? Because for every n, I'm dividing it by 2. So this may have to be 1/2. I'll go ahead and I'll check, and if I wrote this wrong and wrote 2 instead of 1/2, then I'll change it in your reader. If it is, so whatever you see in your course reader will be correct. So apologies if there's any confusion on that right now, but that's the way it works. So what is the actually? So this is actually the exact value, okay? So that Simpson's rule is very, very, very accurate. So if we compare this result to our error table for the other approximation, it's very impressive. Okay, so again, the midpoint rule needed 16 points, right? 16 rectangles in order to be fairly close, but I used 4 and I was exact. So let's look how the error bound works. So let's say that we want our approximation to be within 0.00001. And the closest I got with the midpoint was 0.004. So here there's 3 zeros. So let's say I turn this into a 0 and this into a 1. So, almost so much more accurate than I am now, right? 50 times more accurate than I am right now, right? Using the midpoint, trapezoid, and Simpson's rules, right? So this is what I got from the midpoint rule. Remember, the trapezoid rule was like 0.009 or 0.009 at the same point, I believe. So what size n would I need? How many rectangles would I need to make sure that I'm this accurate with the midpoint, trapezoid, or the Simpson's rule? Okay. So for the midpoint and trapezoid rules, we need the condition that the second derivative is less than some value over my interval. Okay. We don't have a value for k given to us, so we have to kind of figure it out. So in order to do that, let's find the second derivative of our function. Our function is polynomial. That means the first derivative is 3x squared minus 6x. Second derivative is going to be 6x minus 6. If I just kind of look at what that is, right, it's a parabola, right? If I factor it, it has 0, I'm sorry, it's a straight line, okay? And so the largest value my straight line can be between 0 and 1, my interval of existence, is 6, right? If I plug in 1 here, well, if I plug 1 here, I get 6 minus 6 is 0. If I plug in 0, I get -6. Absolute value of -6 is 6. So the largest absolute value that my second derivative is allowed to be from 0 to 1 is -6. So an absolute value of 6. Okay. So I always choose the absolute value of it. So that's going to be k equals 6 in that case. So the size of n required for the error in the trapezoid rule to be less than or equal to 0.00001. So this is what? Tens, hundreds, thousands, 10,000s, 100,000s. So within 100,000, right? If I start to replace everything in here, 6 is k, b is 1, a is 0. So this is just 6 divided by 12n squared. My error tolerance, I need it to be less than or equal to this amount. So obviously I choose the largest amount. And then I just solve for n. So I'm going to divide by 6, multiply by 12. Actually, probably it's faster to multiply by n squared and then divide by 0.000001 and take the square root, right? That's much, much faster. And so when I start to plug these things in, 223.6067977. Now, that doesn't make sense for a value of n. If you plug this into my open math or whatever we're using, you'll get the answer wrong because n is a whole number, right? So I don't round down. I'd have to go up because again, I'm trying to be at least this accurate, right? So I wouldn't say it's 223 because I would not be this accurate because I'm less than the number I need. So I always round up if I need to. So n equals 224, right? I would need 224 rectangles in order to make sure I am within 100,000th of the true value with the trapezoid rule, right? So 4 decimal places of accuracy, right, is really what this means. Okay, I have a little bit of accuracy at the fifth, error at the fifth, but I have to be within 4 decimals of accuracy, which is actually very, very standard for things in engineering and in physics. Okay, for the midpoint formula, we'll do the exact same thing, but we'll use the formula for midpoint, which was 24n squared instead of the 12. So everything is the same. I plug in 0.00001 for my absolute error. K is 6. This goes to is just 1. And then I solve for n squared. Okay. So to no surprise, it's less than half of that, right? Oh, I'm sorry, it's not less than half, but it is very accurate. It's very close, right? So it's 159 I would need, right? So this is 224, so it's not half, but it is significantly less, right? As far as like the number of calculations that we need to use, right? So if you think about writing the program and having to do several, 100 calculations in order to be so accurate, um, if I use the Simpsons rule, I need to take the fourth derivative, right? So my third derivative would be 6, and my fourth derivative is 0. Therefore, we never exceed the absolute value of 0 for the fourth derivative, so we get to choose k equals 0. Okay, so this whole top part just turns into 0. So how many n's do I need? 0, right? Because we saw that I'm exactly right. I got the exact value from the Simpsons rule, right? So remember, n has to be at least 2. So even if I use uh, just one parabola with the Simpsons rule, I would have gone right. So even the lowest possible value of n would give us an approximate answer more accurate than 0.0001. Okay. So from our previous works, we can see that the smallest value of n equals 2 for the Simpsons rule would give us this, right? So 1/3 from the Simpsons rule, 1/2 from delta x. And here I'm just using 2, right? So 2 rectangles was just one evaluation. The leftmost, the rightmost, and then the shared, right? So to do Simpson's rule, I need at least n equals 2, so 1, and that still gives me the exact value. Okay, so even the least amount of rectangles possible for the Simpsons rule 2 gives me a value more accurate than my tolerance, right? Versus if we do the trapezoid rule, which needs 159, or the midpoint rule, I'm sorry, the trapezoid rule, which needs 224, and the midpoint rule, which needs 159. The Simpsons rule needs just 1, right? Or in our case, 2, because I need to have at least 2 rectangles. And that will give me the exact value.